Okay, everyone. Hello, how are you? My name is James Patton Wilson. Going to teach you today how to decipher what maybe I've said already. My name is Patton Wilson, and we have a circle there. Circle which has 1, 2, 3, 4 so-called quasi-dimensions or whatever. You got 1 dot, 2 dot, 3 dot, 4 dot. What I did, you got x equals a, b, c, d, because 1 times 2 times 3 times 4 equals 24. X is omega, or the 24th letter. So, there you go. If you add on an e there, you got 29, which is right up here. And 29 would make things a little bit different. 29, you could minus 24 or plus or do whatever you want with it. But I get the difference of 14 before you go to 29, before you go other numbers, but let's not talk about the 29 much. We've got there are 5 there. Look at that. I already wrote it up there. 2. So that takes care of possibly this. So that's one dimension that I'm talking about. So you got B and C, A, B, C, capital A, B, C. And that is why I said D. O to, D to the function of 0, D, whatever. You would still end up with maybe y, 1, 2, and 3, like they're leftovers, because you got these things right here are kind of like the random relativity of me, moreover, and how they blend in. Because with this, since you can see I've got these tattoos, and I've got 45 of them. So you got my skin too, so let's see, add on 1, type that, and that's 46 chromosomes. So that's like representation of how this could relate to me if I could connect to it. So maybe you've already done that. So then you got these leftovers here anyway. You got 10 from adding up A, B, C, D. Alright? And throw an ink pen. A plus B plus C plus D. So if you were to use this formula or whatever, you could go 1 plus 2 plus 3 plus 4. So you got 10. Here you got the difference of 24. 10 minus 24 equals 14. Or whatever. Or that's the difference. Whatever. Then you got, where do we get D? We got the D's left over just from doing 3, A, B, C, So you could maybe tell a little bit about yourself there. But back to what we were talking about, the lambda eta to the power of iota minus epsilon. There's this thing I've done with it, SLPOE. That's where we are now. You could say this is the space lab planetary observatory of exobiology, because this is where this is our location. Anyway, that's a lambda. That's an eta, because that's a Sagittarius, and that's the Pleiades. You know, M45. That's the 45 tattoos. I can't even write very well. On and on. The Ophiuchus, or whatever, how you want to pronounce that for the O. Because it's kind of a manifold of the 45. I've got 8 clusters worth, so that's 8. So I tacked on the 9 because, you know, the linear you would have 8. 8. So if you had 9, it would be like connecting the dots kind of from 5, 6, 7, 8, like that. So how many would that be? Would they equal each other? Well, they do, but they don't. You know, they're sort of linear, non-linear, so to speak. And that could even be spelled 1/8 equals 2/9, because you could go 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe not do that. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 if you had 9. So that's kind of a string theory thing. There's 2 strings in between, one like that, one like that. And symbolize it. Anyway, it relates to things, and that's, you have to make your world relate so you can make something of the world for yourself. What I was thinking about doing was taking these Y's and spelling X, A, B, C, D, E. And then for a closing message, this is just kind of a K-finder, solver, kind of like a apparatus that detects things, these things. The reason why I did iota, oh yeah, we get the 5, 8, and the 4, 45, 8, that kind of solves that with the 9 for the tattoos down here. And then this is my Planetary Society membership ID, whatever it's worth to you. So I like to write that because I'm the 7th generation of Wilson, so 7. I like that. What else did we do? Oh, my HMH. We gotta take care of everything on the board. HMH, Harrison Memorial Hospital, 41031. I left one of my math books there, so that's my ID there. And so we've got these left over, right? It kind of takes care of everything. Well, we've never even touched on this. So that's 5. So I guess what I'm talking about is about how when you have 4 dimensions in the Minkowski 3 or whatever, there somehow tends to be a twist to where you want to go back to the beginning, like these things. Like if, say, you had 1, 2, 3, so you go 1, 2, 3, 4. you know, or you could transform that to a better understanding of a cube. Three space dimensions, one time dimension, and the cube. 4 dimensions ago. Thank you. Hello, hello. Once again, we have some scratch there. So what I'm going to do is slice this. Write a little equation there. So, if you want to think in terms of the 4 dimensions, well, at least we know for sure we have, at least. Maybe you could say maybe in dimensions. Because we have n minus 1. You'd say that would be space. Maybe. Is there an n plus 1? But anyway. How's that? So how does that mean anything to you? Send your postcards and letters to 941 Allen Pike. Send Vienna, Kentucky 41031. My name is James Patton Wilson. And that's just some random stuff there. I don't know, maybe that could reciprocate this, but I already put that there, so you never know what lurks behind the counter of shadows in the dark. Anyway, that's enough for now. Okay, everyone. So how are you today? We got all this stuff here. I'm back. Almost a solar eclipse, almost coming up very soon. Let's see. It has not happened yet. This is Patton Wilson. So all in all, we calculated to E whatnot at 24 mostly. So if you have the square root of 24, the root of 24 squared, you get this little number, 4.897948556356. If you I don't know which way you can see better, but this is what we did since the camera shut off. Over here, we can make that equal MC squared. Somehow we took the root of 24 because we assigned that 24, you know, the root of 24 squared or whatever. And that's how we got that. So there's a difference somehow too, and somehow not in the relativity of time and space there. Kind of a x plus and a minus to space-time. This one represents something, I don't know, you'd have to chart that out some other way. So it only equals things that relate to whatever you're talking about. At the time you were talking about it, or you wouldn't understand why m times c or squared, mc squared even exists. Mass and a constant, try to find those. Hello, how are you guys and gals today? Here's the new debunkment here. We want to find, I don't know, a little bit about age. And beauty. Quantified as kind of a rite of passage, which is right here. Passage, which is right there. Initiation. Since we've written this all down already, we're going to kind of skip around. So there's one line, one line, one line, one line. So there's 4 and 4, 8, 9, 10, 11, 12, 13. You know, M is the 13th letter. Pardon me. I got sniffles. So, what do we do? Last time we were kind of talking about how N1 minus N1 minus N1, like that, whatever. N1 minus, N minus 1 3 times anyway, multiplied, N plus 1. Somehow, if you could figure out the way to maybe show that it's coming from right there, so right there, plug in X as 24 for the number there, or whatever, you might get a little bit different of an answer. So if you got, well, you calculate that real quick. Because I don't think we'll get the same answer as that with this. We'll see. 23 times 20, 23 times 23 times 23 divided by 25. That's a 486.68. Of course it would be. We multiplied, we did something different. But 486.68. 68. we compared all these things, we can take out the x in here that we use to calculate the x omega. So chart that out if you want. 486 and 552,000. You do a lot with that. X and Y. Let's see. Say a mass that is, that's, oops, E equals mc squared. That's the law that governs physics, so to speak. If you could say M, so right here, let's erase this. Pardon the board, the temperature has changed, and it's changed the purpose of the board, so it's nice again. So E, we want to know some type of E. Comparatively to all this here that we went through, if you pay attention. Say you have 486.68, and then you put this in. Calculate some more energy here. Let's see, 486.68. 550 times 486.68 equals that. Oops. I missed this one. 486. I got this. 2.6864736 to the power of 10. Just what you've seen. So E would be that. Energy, what is some way to know now also about imaginary numbers comparatively? Multiply that out. Let's find a shorter value for this. This will probably be interesting because of where I'm taking this from. E. There's a lot of good e to 100 decimal places. So what's the difference between this Princeton book and what I've calculated? Because they got a 2.71828, and the e that goes to 100 decimal places or whatever. 1884, and you can just go on forever about that. And the source of this was the Encyclopedia Dictionary of Mathematics, Mathematics Society of Japan, 1980, Cambridge, Massachusetts, MIT Press. So, what's the difference? What's the difference here between 2.686476 to the power of 10? Minus perhaps 2718281834. The other one. Got pretty much the same number on that up here. So let's see. 2 point, we'll do it backwards, so to speak. 2.81284 minus 2.6864736 equals pretty much the same number every time I do it, except it just changes it to plus and then what we just discovered here. So how is there a difference? Too much about that. And you can pretty much take this here and some of this and that. Don't really need all that. That's how it relates kind of to 45 though. Plus 1, minus 1, 0, you know. Because you had a difference there between 45 and Google Flex 44. So, how is that interesting? And how interesting is that? So what does this equal? This is more like some type of E. You can change it to kind of maybe final sum or something. I could do this since that's how I found it. I'll do this. And that's about the end. As many times as we can drop it. That's how we present ourselves.
Rotation is turning of Earth around its axis, an imaginary line that runs vertically through the center of the planet. A single rotation of Earth takes 24 hours. It takes Earth's rotation that produces the endless cycle of the day and night. At the same time, it is night on the other half of the planet and day on the other half of the planet.
Okay. Wait a minute.
Early Early scientists looked at Mars through big telescopes. An intelligent astronomer named them candles, but someone read them as channels. So for many years, many people thought intelligent beings had built channels all over Mars. In 1965, Marina forwarded Mars and took a clear picture.
Hello everyone. This is Patton Wilson at Will Allen Acres. How are you today? I hope your day's doing good. We have a lot to talk about. Quite a little bit. And today we're going to go and write a book through quotes. So we'll need to take some notes, won't we? By the way, my authorization member ID is 686657. This is a film by Patton Wilson. Named Sequel. Okay, sorry. Anyway, this is a movie named Sequel. So have fun with that idea. And we'll start you out quoting an imaginary tale, the story of the square root of -1 by Paul J. Nahin. So, there's something about a young adventurous man who discovers an ancient parchment among his late great-grandfather's papers. On it, it reads, "Sail to blank north latitude and blank west longitude, where there wilt find a deserted island. There lieth a large meadow not pent on the north shore of the island, where standeth a lonely oak and a lonely pine. There thou wilt also see an old gallows on which we once were wont to hang traitors. Start thou from the gallows and walk to the oak, counting thy steps. At the oak thou must turn right by a right angle and take the same number of steps. Put here a spike in the ground. Now must thou return to the gallows and walk to the pine, counting thy steps. At the pine thou must turn left by a right angle and see that thou takest the same number of steps, and put another spike into the ground. Dig halfway between the spikes, the treasure is there." That was something by Gamal too. So don't forget to take your notes there. So something else we wanted to talk about
Almost there. This is a book called The Story of a Number, and the story is actually a book by Eli Marr. That I'm trying to figure out here. Anyway, the letter E may now no longer be used to denote anything other than this positive universal constant, the solution of the equation linear line x equals 1. Edmund Landau, Differential and Integral Calculus, said that. So we quoted this also. Infinities and indivisibles transcend our finite understanding, the former on account of their magnitude, the latter because of their smallness. Imagine what they are when combined. Galileo Galilei, as Salviati in Dialogus Concerning Two New Sciences. So, what do you think about that? Huh? What do you think we could do next with that? We could call some other dudes and talk to them. The human understanding is no dry light, but receives infusion from the will and affections, whence proceed sciences which may be called sciences as one would. For what a man had rather were true he more readily believes. Therefore he rejects difficult things from impatience of research, sober things because they narrow hope. The deeper things of nature from superstition, the light of experience from arrogance and pride, things not commonly believed out of deference to the opinion of the vulgar. Numberless, in short, are the ways, and sometimes imperceptible, in which the affections color and infect the understanding. Francis Bacon said that. Novum Organon. There's some more here, you know. But, I don't know. Insight, untested and unsupported, is an insufficient guarantee of truth. Bertrand Russell said that, Mysticism and Logic. I have some more here, but I don't know if you want me to read it. Just thought I'd tell you. We'll get to our thing here. The theological worldview is the idea that the world and everything in it has a good and undubitable meaning, since our earthly existence has in itself a very doubtful meaning. it follows directly that it can only be a means towards the goal of another existence. The idea that everything in the world has a meaning is precisely analogous to the principle that everything has a cause on which the whole of science rests. Kurt Gödel said that. Let me see. The spreadsheet created the What If Society. Instead of moving forward and progressing normally, the What If Society questions every move we make. It second guesses everything. John C. Dvorak said that. But I'll tell you what, here, we'll get into it. The same person prides himself on his ability to be unaffected by important facts and interested in unimportant ones. He refers to this as having a sense of perspective or keeping things in proportion. Celia Green said that. We'll get to some music here in a second, won't we? We'll say something. We'll say something else. There isn't a parallel of latitude, but thinks it would have been the equator if it had its own rights. Mark Twain said that. I don't know if you want to endure this any longer, but I'll tell you, I do not think the paper very important myself, but De Sitter was keeping on it. Albert Einstein said that. And William De Sitter said, "You will have seen the paper by Einstein and myself. I do not myself consider the result of much importance, but Einstein seemed to think it was." What else next? What else next could there be? Now this is interesting, even more than anything. Okay. For three-dimensional space, the theorem can easily be generalized. It states that the sum of the squares of three adjacent sides of a cube is equal to the square of the diagonal. So, if A, B, and C represent the sides of a cube and D is its diagonal length, then A squared plus B squared plus C squared equals D squared. So in other words, the length of a diagonal of a cube is given by a three-dimensional version of the Pythagorean theorem, A squared plus B squared plus C squared equals D squared. By simply adding more terms to the Pythagorean theorem, this equation easily generalizes to the diagonal of a hypercube in n dimensions. Thus, although higher dimensions cannot be visualized, it is easy to represent n dimensions mathematically. Masao Kaku said that. And uno momento for the last of this. The predictions of Newtonian theory therefore match the view of reality we all develop as we experience the world around us. But individual atoms and molecules operate in a manner profoundly different from that of our everyday experience. Quantum physics is a new model of reality that gives us a picture of the universe. It is a picture in which many concepts fundamental to our intuitive understanding of reality no longer have meaning. Stephen Hawking. Stephen Hawking said that with Leonard Mudlenow. And now, presenting what? I don't know. I don't know. We're totally floored here, Patton. Right now. Let's just try to think of something here to explain all of the things we've already explained or something. But Richard Feynman said this. Immediately you would like to know where this number for a coupling comes from. It is related to pi, or perhaps to the base of natural logarithms. Nobody knows. It's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. You might say the hand of God wrote that number, and we don't know how he pushed his pencil. We know what kind of a dance to do experimentally to measure this number very accurately, but we don't know what kind of a dance to do on the computer to make this number come out without putting it in secretly. So, very good number for that. We don't know. I think he's talking about the constant E, which, yeah, that's it. We don't know for sure. What we could say about the number E there. You never can tell sometimes about people. You never can smell sometimes about how good you are. But that's sad, isn't it, ladies and gentlemen? End of the movie forever. We have a recorrection here. The story Imaginary Tale by Paul J. Naheen was not the story of the square root of -1. It's the story of the cube root of -1. Just remember that. And now we will read a real quote by Naheen, Paul J. And We're almost there to the way we've actually done this. We're going to sing a complex number song tune, the Battle Hymn of the Republic. Mine eyes have seen the glory of the Argand diagram. They have seen the eyes and the thetas of Demor's mighty plan. Now I can find the complex roots with consummate elan, with the root of -1. Complex numbers are so easy, complex numbers are so easy, complex numbers are so easy with the root of -1. In Cartesian coordinates, the complex plane is fine, but the grandeur of the polar form of this beauty doth outshine. You'll be raising I plus 40 to the power of 99 with the root of -1. You'll realize your understanding was just second rate when you see the power of the magic of the complex conjugate, drawing vectors corresponding to the roots of -8 with the root of -1. Complex numbers are so easy, complex numbers are so easy, complex numbers are so easy with the root of -1. Complex numbers are so easy, complex numbers are so easy, complex numbers are so easy with the root of -1.
The tide. As the Earth rotates, the high point of a bulge reaches any particular shear line once every 12 hours. The rising water that causes this is called high tide. When the bulges passes and the water goes out again, it's called low tide. The gravitational pulls of the sun and the moon produce the tide, now known as oceans. The pull of the moon's gravity causes the oceans to bulge toward the moon.
nice little while.